Welcome back, everybody, to the Rule Your Pool podcast. I'm your host, Eric Knight with Orenda, and today we've got a new guest, a new employee at Orenda. We're going to introduce him in just a second. In the last episode, we introduced this 5-part series on calcium issues that we get a lot of phone calls on. And I do mean we get a lot of phone calls on them. So calcium issues in general are usually going to be calcium carbonate. And today we're going to discuss the second variation, I guess second and third variations. Last episode we covered scale. And in this episode, we're going to cover calcium dust and carbonate clouding, and we'll explain that. But first, I want to introduce you to our new guy, the FNG, Ryan Rickaby. Ryan, thanks for being with me.
Glad to be with you. Thanks, Eric.
Well, you have a lot of experience in the pool business, and I'm sure you've encountered white discolorations in pools and cloudy water before, so hope to get your opinion on this topic. You ready to go?
I'm ready.
All right, episode 49, let's go.
Welcome to Rule Your Pool, the podcast by Orenda that explains and simplifies pool chemistry so that anybody, regardless of experience, can understand it. I'm your host, Eric Knight, bringing clarity to these subjects so that you can bring clarity to your water. If you're ready to rule your pool, then let's go.
Okay, Ryan, the first thing is there's a lot of different forms of calcium in our water. And we talk about calcium hardness as the amount of dissolved calcium carbonate. And we talk about the LSI as the saturation of calcium carbonate. And in the last episode I was talking, since you probably haven't listened to it yet. Actually, I know you haven't listened to it yet because it hasn't been published yet.
That's correct. I haven't heard it yet.
Oh, it's only in my brain, dude. It's only in my brain. So I gave the analogy of sugar in a drink, that you could put 2 tablespoons of sugar in your drink, and a lot of it's going to sit on the bottom of the drink if that drink is at room temperature. Now, it's still 2 tablespoons of sugar in the drink, but if you were to raise the temperature of that drink and get it close to boiling, it'll easily dissolve that sugar. Same water, same volume of water, same amount of sugar, totally different saturation equilibrium. You tracking so far?
Yeah.
That's the difference between the LSI, which is the saturation equilibrium, and the amount of sugar we're talking about. Because if we were to translate the word sugar into calcium carbonate, we would say 400 parts per million calcium hardness. It can either be totally saturated, or it could be forming scale.
That's right.
Or on the opposite side, it may not be enough. So you might actually be etching. Now, in the case of 400 parts per million, that's probably not the case. But let's say you had 250. If your water gets really cold, suddenly 250 is not enough calcium hardness, whereas at 90 degrees in the summer in Texas, it probably was. That's what we're going to talk about today. In this episode, we are covering carbonate clouding and dust. And these happen in various parts of the year, but when you come across a cloudy pool, Ryan, what could cause that, you think? What could be... other than what we're about to talk about, in your experience, what would you first think? Oh, here's the water's cloudy. What do you think might be going on?
Yeah, it could be, we just had a party in the pool, lack of chlorine. It's probably the first thing that comes to mind.
Mm-hmm.
Maybe
right.
Poor circulation, dirty filter, those types of things.
Mm-hmm. Absolutely. Because particles that are not filtered out, right, solids that you can see will cloud up the water. The technical term, of course, is turbidity. If the water is turbid, it means it's cloudy. But that's a little fancy. I think cloudy is appropriate. Have you ever come across a pool, Ryan, that was not just like dull and gross looking, and greasy and cloudy after a party or something, but it was actually like pure white or gray? Have you ever seen that?
I have not.
Oh, man, you're missing out. Let me tell you, it can happen. And typically when that happens, something changed. Maybe the heater was just turned on. That's actually a very common example. The heater gets turned on, suddenly the spa goes cloudy. And starts to just cloud out of nowhere. And that's what we call carbonate clouding. Now, a more obvious example of this is if you add soda ash to a pool too fast or too much. Have you ever done that?
I have.
What does it do?
Well, it clouds the water pretty good.
Okay, describe it for the listeners.
Well, I mean, it instantly gets cloudy, milky almost,
Mm-hmm.
You can't see the bottom. And you get cloudy water.
Yep, it spreads and spreads. You're like, no. What have I done?
Yeah.
What you're looking at is a localized LSI violation right then and there. You forced an LSI violation. So in one of the key takeaways of this episode is we want to really drive home that the LSI really tells the story on this and all the other parts of this 5-part series. But in particular, we're not talking about the other forms of calcium like we did last time, calcium phosphate, calcium sulfate, that kind of stuff. We're talking about calcium carbonate. That's why we call it carbonate clouding and carbonate dust. All right? The LSI tells the story, but it doesn't necessarily tell the story of what you test that day. So if you come to a problem pool and you test that water, you're looking at a moment in time when the water has had time to balance itself, perhaps at the expense of your plaster surface. We really need to go back in time and we got to think, what could have caused this problem? What originally caused this problem? And then we start looking back. And so if, let's say we've got dust all over the pool. Okay, how did it get there? Well, let's test the chemistry. If there's dust all over the pool, pretty good chance there's a really, really high pH. Okay, where's the calcium hardness? Oh, that's low? The calcium hardness is low, right? So, or maybe it's high. Maybe it was an oversaturation and you had too much sugar in your drink and it just clouded out and it fell as dust. That's possible. Or maybe it was pulled out of the plaster, it pulled calcium hydroxide out, which had a really high pH, and it forced dust to be created, which we would call plaster dust, and that landed on the surface. You can tell these things differently because if it just clouded up and it landed on the floor, it's only going to be on the floor. Whereas if it was plaster dust, it's going to be on your walls too. Now, a lot of it will fall to the floor, but it's coming from a fresh plaster surface. So these are the different ways that we can go back forensically and look at what originally caused this. So I want to get a little bit into the chemistry of what's going on here without glazing over our entire audience. But essentially what's happening here, if you get carbonate clouding or dust, calcium carbonate is coming out of solution. That's it. That's what's happening. Now let's figure out why. What do you think some of the reasons calcium carbonate could come out of solution are, Ryan?
Well, I mean, it's a clear LSI violation. So usually I would think that, and what I've been kind of worried about here in Texas is, the amount of snow that we got, in February of this year. And so it clearly reduced calcium in the pool. And, it forced the LSI to go extremely low, right? And I'm worried about that moving into this winter because, during the summer, it kind of equalized out. Water temp came up and everything was fine. And now as we start to get colder, I think that this could arise with people overlooking calcium in their water and the colder water temperatures.
Yeah, I think you're absolutely right. It changed the parameters. And now, obviously, a winter snowstorm is not typical in Texas, but 2020 and 2021 were not exactly typical years in history to begin with.
Got that right.
So if you couldn't pick a worse time to have a blizzard that caused that much mayhem, 2021 was probably the right time to do it, I guess, for maximum impact of devastation. So yes, snow and rain have zero calcium in them. They reduce the LSI. And water now has to correct itself. Now, if you have a plaster type surface, that means it's going to etch, it's going to eat. And that's going to pull out a very high pH calcium hydroxide, which will then get carbonated, turn white. Okay, the pH spikes and the conditions change. Now, I'm not going to go down this entire rabbit hole. I will tell the audience we do have plenty of blogs on this, but if you search our blog for cover or winter or anything like that, we could talk about how different types of covers affect how you winterize your pool. If you winterize your pool, the chemistry is different. A solid cover will suppress the pH. CO2 can't leave, but dilution also can't get in. So you have to winterize differently. Whereas a mesh cover allows CO2 to escape, so your pH goes up, but it also allows dilution to go in. You have to have a different strategy for that. So now that we've covered that, Ryan, you're exactly right. If you have a winter storm, your LSI parameters change. And back to the original question of why would calcium carbonate precipitate out? The short answer is the water can't hold it anymore. There's just too much. There's too much sugar in your drink. It has to go to the bottom for some reason. And again, if we go back to that analogy of 2 tablespoons in my drink, if we have the same amount of water, if I have this hot water that I dissolve those two tablespoons of sugar in, and then I let that water cool down, a lot of that sugar is going to either congeal to the sides of the glass, and that would be like scale, or it's going to just cloud up that drink. It's going to cloud up that water until the sugar lands on the floor. Now, that is the exact same concept of carbonate clouding and scale and dusting, except the temperature is going to be opposite. Unlike sugar and pretty much everything else that dissolve better in hot water, calcium dissolves better in cold water. So as the temperature goes down, the water is going to eat more calcium. It's going to stay in solution better. It's when the temperature goes up that it starts falling out of solution. That's the big difference. But it's the same concept, just like you could do in your drink. It's too sugary, it starts getting thick and it falls out and sticks to everything. Well, yeah, replace the word sugar with calcium carbonate, you get the idea. Now let's talk about what could actually change that besides temperature. I gave the analogy earlier that if you turn your spa on and you take your, 55 degree water in Texas right now in December, maybe it could be colder than 55 right now. Let's say it's 50. And you raise it up to 90, that's a 40 degree temperature swing in an hour or so, right? Or less.
That's right. Yep.
Huge difference on the LSI. Absolutely huge difference on the LSI. And you're bound to get, if your LSI parameters aren't allowing for that, you're bound to get some cloudy water in that spa. You've probably seen this before.
Yeah, I have. Yeah. As soon as that water spikes up, it precipitates out. I mean, It's going to cloud the water.
Well, and it's also going to put scale on the tile line and all these other things because right then and there, you are witnessing an LSI violation before your eyes. The more extreme example, as we talked about before, is throwing soda ash in your pool. So I'm going to share my screen here. I'm going to show a little bit of what's going on there. And let's see, share my screen. Now, for those of you listening here, all of this is available on our website. Okay, so I'm showing the alkalinity equilibrium in swimming pools chart. It is in every article that we talk about alkalinity and then some. So if you go to blog.orendatech.com and you just type in the word alkalinity, you will find this chart. It looks like a 3 waves and carbonic acid, bicarbonate, and carbonate. This is the equilibrium that determines the type of alkalinity you have in your water, and it's based on pH. The higher your pH goes, the more hydrogens jump away and dissociate from the chemistry. And so, for instance, when CO2 dissolves in the water, CO2 plus H2O is carbonic acid, H2CO3. As the pH climbs, one of those hydrogens, you have 2 of them, one of those hydrogens jumps off. And I think those of you watching this can actually see this H2CO3 becomes an HCO3 with a negative valence because the hydrogen left. That's called bicarbonate. And bicarbonate ions are the vast majority of what we have in our pools as part of our buffering system against acid. This is what we measure when we're measuring total alkalinity. We're measuring, bicarbonate, carbonate, cyanurate alkalinity, and a few others. But this is the vast majority of the stuff. No problem. This combined to calcium, and it could be calcium bicarbonate, and it's dissolved. It's totally clear. Everything's kosher. Unless your pH gets too high. And at 8.3, what happens is bicarbonate ions, HCO3, lose that last hydrogen, and they become carbonate ions, which is just a CO3 with a double negative valence. Here's why that's significant, Ryan, now that the chemistry, I feel like Bill Nye trying to explain this stuff sometimes, but this is as complex as it gets, folks. Don't worry. Everything's easier from here. The only reason I'm sharing this is because when the pH gets high enough, carbonate ions, CO3 with a double negative, perfectly align with a calcium ion, Ca++. So CO3 minus minus marries up perfectly with Ca++. You get calcium carbonate in many different forms. So if your pH gets over 8.3, you are bound to get some clouding. You're bound to get some scale. You're bound to get something that's going to happen just inevitably because you now have bicarbonates converting into carbonate ions. That's what's going to bind up. That's what's going to precipitate calcium. Now, you can actually avoid this if you bind up calcium itself. This is the key. So if you use SC1000, for instance, and you actually chelate the calcium in your water, that calcium's spoken for. It's not going to have the ability to be carbonated because it's not a Ca++ anymore. It's actually bound. It's a chelated compound now. So carbonate can't actually bind with it, and you're not going to get that scale the same way. That's why our product is a scale inhibitor. It interferes with that marriage between carbonate and calcium. That's why that happens. So when you get this precipitation, it will start clouding up. Now, you may not see that because you may not be paying attention. It may be at a very microscopic level. But if it's dramatic, like turning on your spa from cold water to hot, you will see some cloudiness unless you have something like SC1000 already in your water and all that calcium's already spoken for. This is actually a bigger problem on cal hypo pools because they're constantly introducing new calcium. And if you're not maintaining with a chelant or sequestering agent, there's a lot of calcium that's not spoken for. And that's the calcium that's going to come out of solution, most likely. Back to soda ash. Ryan, when you threw soda ash in, how fast did it cloud? Or are we talking minutes or are we talking seconds?
It's fast. It's fast, and it accumulates, and it just keeps going.
It keeps spreading, right? Like a mushroom cloud. You can't
look
away, but at the same time, you're like, I hope the homeowner doesn't see what I just did.
Yeah.
Well, you actually can stop it. Take a guess. Now, I'm putting you on the spot here because this is not in the show notes. What could you maybe do that could reverse this? What could stop that cloud in its tracks?
Probably muriatic acid.
Oh, ding, 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 ding. Look at the big brain on Ryan. That's exactly what you can do because you are reversing what we saw on that alkalinity chart. We are bringing the pH back down and we are converting carbonate back into bicarbonate or even carbonic acid, which lets go of the calcium so it goes back in solution. That's very good. Yeah, so you can actually reverse it in a pinch, but you're wasting soda ash and acid in the process. But you can absolutely clear it up and stop that in its tracks. Another way you could do it, like I said, you could chelate all the calcium in your water, so when you put soda ash in, it doesn't have any free calcium to bind to. But soda ash in particular is different from sodium bicarb because soda ash is technically sodium carbonate, not bicarbonate, sodium carbonate. And as we saw from that chart, carbonate ions don't have a hydrogen on them. So when you put free carbonate in that water directly without having to convert others, number one, you're introducing a whole bunch of new carbonate that the water never had, and it's looking for all the single ladies. It's looking for all that calcium that's available that's not already married to a chelating agent or a sequestering agent. And anything that it sees, whoo, buddy, marries up, clouds out immediately, and that's the cloud that you see. You are looking at an LSI violation in real time. It's kind of cool when you think about it. It's also really stressful when you're the one that's responsible for it. Would you agree?
Yeah, that's true.
Yeah. Not so fun when you're the one in the backyard realizing, oh, wait, I thought this was sodium bicarb. Oops. They are different chemicals, by the way. Soda ash is way different from sodium bicarb. But that's what's happening. You're introducing a whole bunch of carbonates. There's another thing happening, though, too. The pH of soda ash is 11 and change. I think it's 11.2 to 11.4, depending on the purity. And different sources have different opinions on what it is, but everyone agrees it's 11 something. Well, 11 pH is a lot higher than 8.2, isn't it, Ryan?
Yep.
So if I put 11 something pH in the water, it's actually going to convert bicarbonates into carbonates. Right there, like right where you poured it. Not everywhere in the pool, but right there in a localized way. Now you have extra carbonates being created from the water, not just what you added in. So you have way more carbonate alkalinity locally, and that's what's looking for calcium. It's going to turn pure white. It's going to cloud up your water, and boom, you get carbonate clouding. Now, I think we've beat the carbonate clouding thing pretty much like a dead horse. Is there anything you want to add before we move on to dust?
No, I think we covered it pretty well, actually.
Okay. Now, the next phase is what happens to that cloud, right? It's got to go somewhere. It can't just stay cloudy forever. It could stay cloudy for a few days, though. I've seen that. But eventually, it's either going to go back in solution, it'll get filtered out and calcify your filter in the process, or it's going to precipitate out as dust. And that's what we're going to talk about now. I know of at least 3 different types of dust. I'm sure there's more, but these are the 3 main ones that we encounter at Orenda. The first one, the biggest one, because we're in the startup business, is plaster dust. Now, Ryan, what's your understanding of plaster dust? You've been in this industry a long time.
Well, it's when the calcium is pulled out of the cement, and it's in the water now, and it's all over the place, and it's a big mess and causes a lot of problems.
In your experience from startups, plaster startups, of course, not vinyl liner and fiberglass because they don't have calcium-based finishes. But if you have plaster dust in those pools, by the way, call us. We need to talk. That's crazy. But plaster dust in a cement-based finish, yes, pebble, quartz, plaster, anything like that. How often would you say there's plaster dust on a traditional startup? Like, what percentage of time? Is it 50-50 your chances of plaster dust, or is it a majority?
It's majority. It's almost every single time.
Mm-hmm. That's my experience too, yeah. And the reason for that is raw water tends to be aggressive. Raw water meaning tap water that has not been pre-treated. This is why we advocate for the Orenda startup, which is basically just LSI balance ahead of time as you're filling the pool. But the reason that plaster dust happens is that raw water's hungry. And it's not going to wait for the whole pool to be full before it starts eating. It's not like the water's talking to itself like, all right, guys, just wait. We're only halfway full. We're going to have a buffet here when we get to the tile line. Just hold off, guys. That's not what happens. If you look at a colored plaster pool, like with pigment in it, the lightest part of the pool is typically around the main drain. Well, yeah, pools fill from the bottom up. I've never seen a pool fill from left to right. So it's going to have more time to eat near the main drain. The water's trying to balance itself, etc. And when it pulls hydroxides to the surface, those surfaces turn lighter. They turn white because that hydroxide gets carbonated. It turns into calcium carbonate. Oh, yes. It all ties together. We've come full circle, people. It turns into calcium carbonate. It turns light. Now, when it pulls those hydroxides out into the water, because the water's starving for calcium if it's LSI deficient, what do you think was supposed to happen before the water stole that out? I mean, in a perfect world, Ryan, how do we want that plaster to cure?
We want it to cure from the outside. I mean, we want it to get hard, and we don't want to, extract calcium out of the pores of the pool.
Say that again. Pores. Expand on that. We don't want to extract calcium out of the pores of the pool. Explain that.
So what I mean by pores is, calcium as it's curing, it's open, so you have these microscopic things that you can't see that you're drawing calcium from the cement of that pool throughout those small pores, and it's usually everywhere. And the crazy thing is you can't see it. I mean, sometimes you can't see where it's all coming from,
Right. Well, it's microscopic, and that's a great analogy. That's why I had you reiterate it. Think of your face. Think of exfoliating the pores on your face, like your nose and your cheeks and all that stuff. And if you ever have blackheads, I mean, I had a lot of acne as a teenager. What happens is oils are trying to get out of your face. They get jammed up because of dirt and whatever else, and you get acne. It's awful. I'm really glad I got past that phase. But every now and again, you can get a blackhead. You can get a zit. You can get something like that. Well, cement has pores too in its infancy. While it's trying to cure, it is a very porous material. Now, as it hardens, basically the hydration process, it happens on the truck. You mix dry bags of cement with water. You get new compounds created. It starts to get hard as you trowel it into the pool. But as that water leaves, the material loses density and it shrinks a little bit. And so these pores open up. You've got these microscopic cracks and fissures and holes and all this stuff. Ryan's exactly right. There are pores in this cement. And calcium hydroxide takes a lot longer to cure compared to the other compounds in cement. So over 30 to 60 days or so, what is supposed to happen is calcium hydroxide supposed to weave its way and knurl its way all through all that aggregate and all those little channels and crevices at a microscopic level and then harden and reinforce the strength of that concrete. but then you put raw water in it. And instead of allowing it to fill those gaps and harden, like epoxy could reinforce a concrete wall, the water sucks it out. And now you have open pores. Now, when you pulled that hydroxide out, unfortunately, you can't put it back in. And so that hydroxide was supposed to carbonate and harden in the cement, but instead it was pulled out of the cement. The high pH caused an LSI violation, which carbonated it outside of the cement as dust, and that dust landed on the surface. That's plaster dust. Ryan, another visual I will give, every speck of plaster dust, and you've brushed it a lot, I know I have too, it's a lot of dust. It's a surprising amount of dust that comes out of that concrete. Would you agree?
Yeah, it's a lot. It just seems like it keeps coming.
It will keep coming unless you get the LSI balanced and you're able to, cook that steak, as I like to use as an analogy, until you can cure the plaster. It's a lot more dust than it seems. And you brush it up, you're like, oh my God, where did all this dust come from? Well, at a microscopic level, it was being leached out of your surface. Every single speck of plaster dust was supposed to be in your cement, hardening the cement. And when you think of it that way, you start realizing, oh my God, what have we been doing to this concrete? We've been weakening it at a microscopic level, but at a grand scale. So just because you can't see it with your naked eye doesn't mean it didn't happen. If you saw dust, it came out, period. Now, the next form of dust is actually going to be the result of carbonate clouding. All right, carbonate clouding is just you had too much sugar in your drink, you had too much calcium carbonate, and you had a high LSI violation, basically. And as we discussed in the last episode, 48, I believe, the first part of our 5-part series, scale is the result of an oversaturation of a calcium compound that falls out of solution. It came from the water, in other words. Carbonate clouding comes from the water. Okay, it's forcing calcium out of solution because the water can't hold it anymore in those given parameters, at that temperature, at that pH, at that alkalinity, with that much CYA, at that TDS. The LSI dictates this. And if you have a LSI over positive 0.3 on the Orenda app, the number goes purple. Purple means you have too much calcium carbonate in those parameters, and you're going to start getting some that falls out. Typically, carbonate clouding is one of the first things. So carbonate clouding can fall out and turn into dust as well. And that can look like plaster dust. Now, the big example of this is what we call snowing. And I know I'm coming up with a lot of different words, but snowing is on a startup. And if you use the Orenda barrel and you're adding, let's say, 50 pounds of calcium chloride to the startup, and maybe you waited too long and the water in the bottom of the pool had already been etching for 20 minutes as it's been eating that cement, and it's got a much higher pH now, let's just say. You start throwing in calcium. Well, that water is probably going to cloud up pretty quickly because it already has a very high pH, which means it has a lot of free carbonates in it, which is probably going to bind up to the calcium that you're adding. And it's not plaster dust that you're going to see. It's going to be the calcium that you just put in that came right back out of solution and landed on your floor. A perfect example of this was we had a customer raise the calcium hardness up to 300 on his very first startup. Shout out to you, Joe. Very first startup, and it snowed everywhere, like bad. I still have pictures of it. I put it in my presentation. It's on our website too. Snowed like piles of dust. And he said, you know what's really weird? I set this pool to 300 calcium, and now it's 210. I was like, yeah, you're looking at 90 parts per million on the floor.
That's right.
But the pH never spiked, Ryan. That's how we know, because if it was plaster dust, the pH would be through the roof,
right? Because
it ate calcium hydroxide. pH didn't spike. pH was under 8. What happened was he just added too much. It wasn't fully chelated prior to, and we've since learned from that experience, and that's why we keep getting better in the startup. But that's snowing. That is carbonate clouding that fell out. That's all it is. It's not plaster dust, but it does look the same, and it's the same compound, so it gets confusing. Now, Ryan, what is one other type of dust that we've encountered? I know you're new to us, but we've talked about it before, and you're a Texas guy. You're not from the Northeast or the Midwest, but in very cold climates, what's another type of dust?
You know, I'm not too sure. What is it?
You're not too sure. Take a guess. What might happen in the wintertime? I'm totally putting you on the spot. I get that.
I mean, what I'm familiar with is, aggressive water. That's what I'm familiar with in the wintertime when the water drops and the calcium, is too low. It hasn't been properly looked at, and we have an aggressive situation that can rebound, and we have issues from that. But
no. You're exactly right. Everything you've said is exactly right. And it creates something that we call winter dust. Everything you just said, aggressive water going in, not factoring for the LSI in cold water. The water gets aggressive as the temperature drops. It pulls stuff out, and you get the consequences of that. And the rebound, great word, by the way, that is the exact word. The rebound of pH causes what we call winter dust. Now, I'm going to share my screen for the viewers, but for those listening, just type in dust on blog.orendatech's search bar, and you will find it. Let's see here. Here we are. Boom, calcium dust. Now, we have a whole bunch of examples here, plaster dust, but here's winter dust. Now, a way that you can tell winter dust is if you look closely, if there's aggregate in that cement, if there are white rings around aggregate. All right, we have this photo here that show you, let's see if I can zoom in. Oh yeah, we can. Little white rings around every piece of aggregate because that's where the highest concentration of calcium hydroxide is. That's what got lost. But here's the thing about these pools. When you close it, by the way, winter dust usually happens on covered pools, not open pools. When you close that pool, it probably looks really good. And then it gets colder and colder. And yeah, it's going to start etching. It's going to start pulling stuff out of the cement. It's going to try to balance itself. And by it, I mean the water is going to try to balance itself. And it'll pull out some hydroxide. But by and large, the water is clear. There's no dust because the water's cold. And cold water dissolves calcium better, so it holds it in solution. And it eats until it's full and LSI balanced, then it stops eating. Now you're in January, in the coldest part of the year probably. Everything is fine, all quiet on the western front. And then the temperature starts to rise. And you've got a high pH because of the loss of calcium hydroxide. You've got a ton of calcium you didn't winterize with that came out of the surface. And the temperature's going up. And up. And up. And by the time you get there in late March or April, it's probably a good 20 degrees warmer than it was. Maybe more, 30 degrees. And now you start to see something called winter dust because the LSI parameters changed. The temperature goes up. Now suddenly it's an LSI violation and dust starts precipitating everywhere. Here's a photo of it on the website. This is what winter dust looks like. That pool in the photo looks gray with a big pile of white dust on the bottom, but it was actually a midnight blue 6 months prior when it was winterized. Midnight blue, brand new surface. So that's the point here. You can have calcium carbonate in many different forms, but it always has to do with an LSI violation. So just as a quick recap, Ryan, the LSI, it's telling us the saturation of calcium carbonate, right?
Mm-hmm.
It is only a moment of time when we test right then and there. But we can go back in time and say, you know what? We're just getting out of winter. Cold days are behind us. And we can figure out what happened because it was colder yesterday than it was today if we're doing this in the spring. It's the opposite right now. We're in early December. Yesterday was warmer than it is today. So we can look ahead and we can predict what's going to happen based on the water temperature, which moves our LSI strategy. But at the end of the day, if you have an LSI violation now or in the near future because of the parameters that are going to change, you could get carbonate clouding or dust. It's still just calcium carbonate. You had too much in solution. It's an LSI violation. As Ryan so accurately put, if you have aggressive water and it pulls out hydroxides from the surface, you will get a rebound. And that can cause that violation. Yes, you heard that right. A low LSI violation can absolutely cause a high LSI rebound violation. Happens all the time. If you have any of these issues, get your LSI in line. Get your calcium level to a point where you can balance it well. And if you have further questions, reach out to us, info@orendatech.com. You can contact us on social media. You can comment in the links below this video. We try to be as responsive as possible. We're not hard to reach. Ryan, is there anything you'd like to add?
Oh, not really. Other than, the industry's changing at a rapid pace. We have one thing and not the other. So, prevention in water care is number one. If you're not familiar with the Orenda LSI calculator, get familiar with it. Here in Texas, I did mention that we had a bunch of snow in February of 21, and we went into summer with really no real issues. But going back into winter, make sure your calcium levels are where they need to be. Don't overlook that. Don't be afraid to add calcium. That's what I find is people kind of overlooking that reading. They're just testing the range chemistry, and but dive into it a little deeper. You'll save yourself a lot in the long run. And then back to chemicals, cal hypo is something that's it's harder to get right now. So in Texas, they've been adding calcium regularly for years and years through cal hypo. And now, they've gone to liquid chlorine. So just another thing to keep an eye on. That's just what I wanted to add.
Mm-hmm. Yeah, all good advice. So best practices here, yes, maintain your LSI. Do not overcorrect, meaning don't put too much acid in your pool, and always dilute the acid that you do. You need to dose correctly, because this is probably the biggest cause of this is overcorrecting. Too much acid in the pool, you get a rebound, which forces the high LSI violation. Point number 2, get a thermometer, use it. Know the temperature, predict the temperature. That's the second biggest cause of LSI violations. And I would say, finally, just be focused on the holistic view of chemistry in general. Don't dwell on trying to maintain a 7.4 to 7.6 pH, or I have to have 80 to 120 alkalinity, or I have to have such and such. No, it's all about the LSI. It always was. I'm Eric Knight with Orenda, and this has been Ryan Rickaby, our new guy. And Ryan, I will tell you, I put you through the ringer because I did ask you a few questions that are not on the show notes, and I wanted to see how you did. I think you did pretty well.
Oh, thanks, Eric. I had a good time.
All right. Well, thank you very much. This has been episode 49 of the Rule Your Pool podcast. We've got 3 more to go in this, and we'll see if Ryan can survive for one of those, but we'll see. Everybody take care. Thank you so much.
Thanks.
Thank you for listening to Rule Your Pool, a podcast by Orenda Technologies. For more information on what we discussed in this week's episode, check the links in the description or visit www.orendatech.com.
I hope you find this show valuable enough that you tap that subscribe button and share it with your friends. You can also like us on Facebook and social media. And with our help, you'll be able to rule your pool without over-treating it with chemicals and wasting money. I'll see you next episode.